Ever get the feeling you're being watched? Well, in a way, you are. Billions, no, trillions of tiny particles are zipping through you right now. You can't see them, can't feel them. They're ghost particles, neutrinos.
They really are like phantoms, almost massless, no electric charge to speak of. And they basically never interact with anything, which is, well, pretty strange when you think about it.
So that's what we're diving into today, these mysterious neutrinos. But, like, why should we even care about something so elusive? I mean, if they just pass right through us, what's the big deal?
Think of it this way. Imagine a particle so small it can travel through, like, light years of lead without hitting a single thing.
Light years of lead,
It's
that's
a mind-boggling distance. And neutrinos just zoom right through it. They're born in these crazy events out in the cosmos, carrying secrets from across the universe.
Okay, so cosmic messengers. Tiny little spies.
Something like that.
All right, before we get ahead of ourselves, back up a bit. For those of us who didn't ace particle physics, what are neutrinos exactly?
Simplest terms, they're subatomic particles, meaning smaller than atoms, way smaller. Like, think of the tiniest thing you can imagine,
A grain of sand.
even smaller, and then shrink it down a million times. That's the scale we're talking about.
Okay, my brain's already hurting. So how did we even discover these almost invisible things?
Yeah, good question. It's a classic science mystery, right? Back in the 1930s, physicists like Wolfgang Pauli, they were stumped, studying radioactive decay, and it seemed like energy was just vanishing.
Vanishing.
Poof, gone. It broke the laws of physics, or at least the laws as they knew them.
So where was it going?
That's what they wanted to know. Pauli figured there had to be something else there, something carrying away that missing energy, something so stealthy they couldn't detect it. He called it a neutron, but the name neutrino stuck eventually.
So these ghosts, they were the answer to a problem. That's kind of cool.
Exactly. Though, they didn't stop it just being hard to find. Oh no, neutrinos had more tricks up their sleeve. Turns out they can change their identities, what we call neutrino oscillation.
Hold on, change identities. Like some kind of quantum chameleon.
Uh-huh. That's a good way to put it. But instead of just color, they shift their whole form. They come in flavors, electron, muon, and tau.
Mm-hmm.
And they can switch between them as they fly through space. Even through us, actually.
So shape-shifting cosmic ghosts, I'm not sure if that's cool or creepy.
Bit of both, maybe. But here's the thing, that shape-shifting, it tells us something huge. Neutrinos must have mass.
Wait, I thought you said they were almost massless.
We're talking incredibly tiny here, almost nothing. But the fact they oscillate, it means they got to have some mass, however small.
Ah,
And that, well, that changes how we see the entire universe, how it formed, how it works. It's a big deal.
so small particle, huge implications. Got it. I think I'm starting to see why this is worth a deeper look.
Oh, you're just getting started.
All right, so we've got these shape-shifting, possibly universe-altering particles, but they barely interact with anything. So how do we even study them? It's not like you can just, catch them in a net.
Ah, yeah, good luck with that. Neutrinos, they're tricky, passing through planets like they're not even there.
Right, like phantoms. So how do you even begin to catch something like that?
Well, you need a special kind of trap. Forget nets, we're talking giant detectors, often buried deep underground.
Underground? Why go through all that?
It's all about blocking out the noise, you see. Cosmic rays, other interference, you got to get away from all that.
Mm-hmm.
These detectors, they're like ultra-sensitive microphones, listening for the faintest whispers from space.
So giant underground microphones, got it. But what are they listening for? How do you actually detect a neutrino?
Patience, my friend. See, these detectors, they're often filled with huge amounts of ultra-pure water, or sometimes this special fluid. And every now and then, once in a blue moon, a neutrino will hit an atom inside.
Yeah.
And it makes a tiny flash of light or a burst of energy. Really, really tiny.
That's what the detectors pick up on.
Exactly. It's like finding a single firefly in a fireworks show. Not easy,
Yeah.
but our instruments, they're up to the task.
That's amazing. But all this effort, it's got to be for something. What are we actually learning from these neutrino whispers?
Well, for one, they might be able to tell us why we're even here at all.
Okay, that's a big claim.
It's all about the matter-antimatter asymmetry problem. Basically, our understanding of the Big Bang, it suggests the universe should have equal amounts of matter and antimatter.
Antimatter. Isn't that like the evil twin of regular matter?
Sort of. Every particle has an antiparticle, like its mirror image. Same mass, but opposite charge. And when they meet, boom, they annihilate each other.
So where did all the antimatter go? We seem to be doing okay with matter over here.
Exactly. That's the million-dollar question. And neutrinos, with their whole identity-changing thing, they might just hold the answer.
You're saying these little ghosts could explain why anything exists at all?
It's a possibility.
Yeah.
And that's just one piece of the puzzle.
So neutrinos, they're potentially explaining why we even exist. But we were also talking about stars, right? How do these tiny particles factor into something as massive as, well, a star?
It's a numbers game, really. Even if one neutrino's not much, stars, they churn out these things like crazy. It's a flood, a constant stream carrying away energy. Think of it like the star's cooling system.
Stars have a neutrino cooling system. That's wild. I always thought it was just light and heat escaping.
Oh, there's plenty of that too. But it all starts with fusion, right? Deep inside the star, hydrogen's fusing into helium, huge pressure, huge energy released.
Right, the basics of how stars work.
Exactly. But some of that energy, a good chunk of it escapes as neutrinos.
Yeah.
Straight out of the core, almost instantly, like a pressure valve.
So without the neutrinos, stars would, what, overheat? Explode?
Something like that. They wouldn't be nearly as stable. Neutrinos are key to the whole process.
Wow, okay. Tiny particles? Keeping giant stars running? That's pretty amazing.
And it gets even more dramatic at the end. When a star dies,
Supernova.
bingo. When a star runs out of fuel, can't hold itself up anymore, core collapses, boom, supernova. And guess what plays a starring role?
Neutrino.
You got it. The collapsing core, it releases this insane amount of them, way more than the sun will in its entire life. And that burst, that's what helps blast the star apart, makes the supernova as bright as it is.
So they're there at the beginning helping stars burn, and at the end, making them go out with a bang.
Poetic, isn't it? And with every supernova, those neutrinos, they carry information out into the universe, like little witnesses to an incredible event.
This is blowing my mind. We've gone from these things being practically undetectable to, like, the key to understanding how the universe works. What are the big mysteries, then? What are neutrino scientists working on now?
Well, we know they have mass, but how much mass? Exactly. That's a big one. And it ties into everything, how they oscillate, their role in the early universe.
Weird math.
And maybe even clues about dark matter.
Dark matter, the other big cosmic mystery.
It all connects somehow. That's the beauty of it. Every answer leads to more questions, and neutrinos, they just keep surprising us.
From ghost particles to maybe explaining the entire universe. Who knew? This was fascinating. Thanks for taking the time to break it all down.
Anytime. Neutrinos, they're definitely worth a closer look.
Absolutely. And for anyone listening, keep exploring, keep asking questions, and we'll catch you next time on The Deep Dive.